All right, welcome back. Let's talk about two completely different concepts today: multi-core processing and then Git and GitHub. So it'll be a fun one. Let us get started and talk about multi-core first. So nowadays, we don't have just one CPU on our inside of our computers. We have multiple cores, multiple CPU cores, and the way that we got here has to do with something called Moore's law. And so it is a hypothesis that ended up being true. It was like a prediction made by Gordon Moore, who is a very famous man. He was the co-founder of Intel, okay, very famous company, right? He predicted back when the company first got started in 1965 that the number of transistors that you could put on your chips was going to double every 2 years. That's what he thought, that's what he predicted, and that is what ended up happening for decades. Okay, so the number of transistors kept going up, and because things got smaller and smaller, you could like propagate electrons twice as fast, kind of, and that meant that the clock speed of your computer also went up as you made these transistors smaller. This was true for a very, very long time, and so like all you had to do was wait another 2 years, and your computer that you could possibly go out and buy, you'd be able to find one that's twice as fast as your current one. And we know that's not true anymore, sadly. So at the start, like mid-2000s, there were issues. You couldn't make transistors too much, or you could make them smaller, but you couldn't make the clock speed too much faster because there were issues powering those tiny things and dissipating the heat that came from powering them and making them go fast. And so in 2005, we hit power wall, we say, and everybody's clock speeds maxed out at like 4 gigahertz, which means our processors can run and execute about 4 billion instructions per second, and that's still true to this day. Okay. Another issue when you make transistors so small is that you run into quantum effects because you can only put so many electrons in such a tiny place, and so that's another thing that the CPU makers these days have to worry about, which is fun to think about. But because of that, because we can't make individual CPUs much faster, we just decided to stick a bunch of CPUs inside of our computers, and that created the multi-core era, which is where we live today. And so yeah, we just ended up, okay, we decided to just put more CPUs on our chips, all right? More CPUs in your CPU to keep Moore's law going. And we can still double the transistors, but we can't just make things twice as fast anymore. All right, we can just put more CPUs, and so we can run more things parallel, and hopefully that gives you a little bit of a speed up at the same time. All right, so here's a good graphic from Wikipedia. I'll have to update this one day, but if you zoom in, on the x-axis is dates, so years, increasing every 2 years. And then we have a log scale on the y-axis for transistor count. And because it's a log scale, that means if you see a line, if things look like they're going in a line, and they are, that means it's really an exponential increase. It's doubling, like we're trying to say here. So Moore's law is true. Do you see how true it was over time? Each of these points are individual processors and the number of transistors that were in them. All right, so back in the day, the very first like Intel processors, down here we go, had like just a couple thousand transistors. Oh man, that's crazy. Motorola 6800, that was a competing processor back in the day, and like I think the 68,000 was the important one that first got into like some of the first Apple computers. So really, really cool things back here. Intel 8080 is another big one you might want to look into. But yeah, we were down in the 70s, getting close to the 80s. We're talking about 50,000-ish transistors at best. And yeah, as we scroll more and more, we slowly make 100,000 transistors in an Intel processor. Have to wait till like the 90s for the Pentium processors, and now we have millions of transistors. At the same time, though, as Intel processors, you see that ARM processors came out. And like Intel was CISC, right? And ARM was RISC. And they were competing with each other, and ARM had fewer transistors, but they were trying to do the same amount of stuff. And they won. The processors were cheaper. Not only were they cheaper, they were competitive with the Intel processors. They were simpler, and so fewer transistors, which made them cheaper. But they were also like going toe-to-toe with like 10 times more transistors in the Intel processors, which is a really cool thing to think about. And so RISC has a lot of history to it. All right, and so if you keep scrolling, like you have processors that I am kind of familiar with. I remember Pentiums from my my early childhood, and yeah, we're slowly getting to tens of millions of transistors per chip, and slowly but surely then AMD comes on the stage, and if you've heard of them, all these fancy transistors, and around this time is when we hit the power wall. Oops, 2005-ish, we hit the power wall, and so you got these fast Pentium 4 processors, but we want to get more than hundreds of millions of transistors. That eventually means we start having to add cores, and you'll see Core 2 Duo processors come on the stage. So now you have 2 cores per chip. So you're doing, got 2 CPUs on a chip now, and then we have quad core, and that's when all the multi-core stuff takes over. All right. If you zoom out here, you can see that present day we're at the level of, like, now we can put 72 cores on a chip. We're still doubling transistors. We're still mostly following Moore's law. We're up to like 50 billion transistors on a chip. But the way that we get there now is by adding cores, 32 cores, 72 cores on our server processors, so that we can run like 72 programs concurrently, but still max out at 4 gigahertz per core-ish. Okay, so that's where we're going, and that is not changing. It's probably not going to be changing for our lifetime now. That's what we're stuck in, unless we have a huge breakthrough in like quantum computing or something. So yeah, that's Moore's law, and that brings us to multi-core. Let's talk about that. All right, so a multi-core processor contains a bunch of complete CPU cores that can do their own thing. All right, so like on your processor chip, there are multiple individual CPU cores that each can do their own thing. They have their own registers, they have their own ALU, they even have a little cache just for themselves, and they're all separate. They can each be running. If you have N cores, like if you have a 4-core computer processor, then you can run 4 programs at the exact same time, because all of these cores are independent from one another. Okay, that's the idea. And there's plenty more than just, like, if you have a 4-core processor, there's plenty more than just 4 programs running on your computer at once. Like, here's all the programs that are running on my computer right now, all the processes, hundreds. And so they're all getting a share of the CPU time. They're getting scheduled, we say. The operating system is taking care of that and making sure that everybody gets their fair share of time running on the actual CPU. They go to sleep for a little bit, and then they wake up for a little bit. Okay, yeah, so everybody's just taking turns, kind of. And we'll talk more about caches later in the class, but there's caches on the actual CPU cores, as well as some cache memory that they share that's a little bit bigger. Okay, and that's to just hopefully never make it so that we have to go to memory all the time. Go to memory as infrequently as possible is the goal. Okay, so yeah, let me just show you an example of taking advantage of multi-core processors. I need to show you, like, we've never done this yet in your computer science career. You'll probably have to wait until you get to like an operating systems class to fully take advantage of it. But let me teach you how to write a program that runs on more than just 1 core, because every program we've written in our computer science career up until now probably runs just as fast on a 1-core machine as it does on a 1,000-core machine, because we're not using multiple cores. We're just doing we're executing 1 program. Okay, so let's fix that. All right, so first of all, a single program running, I think I said this before, it's called a process. That's a fancy term for it. That's what it means for a program running on your machine. It's called a process. Okay, there is a syscall. There's a syscall called fork, all right, which kind of makes your program branch off, and it like creates the little children of your process. Okay, so there's a fork syscall which you can run. We're just going to run it in C or C++, and that will duplicate our current process. So there's 2 versions of our process running at once, and they're going to each get scheduled on likely different CPU cores and run at the same time. Okay, that's the goal. We are going to write a program so that when we run it, /a.out or whatever, we have our current original parent process, and it's going to fork itself and create a copy of itself called the child process, and we can have the child do different things than the parent. All right, and that's going to be the goal. When you make this fork syscall, if you look into this, there's a manual page for it. Man fork. It's this function. It lives in this header. It's fork, and it gives you back a process ID type. It's just like an integer number. And yeah, it duplicates the calling process, and it returns a number that corresponds to like the process ID of what it just made. So if we happen to be the child program that just got born from the parent, it will be 0. It will return 0, and so we know that we were the duplicate or the clone. Otherwise, if we're back in the parent's version of the program, because there's going to be 2 versions of our program running at once, remember, I'm about to do that, it'll give back the process ID. You'll see something different, okay? The process ID of the child if we happen to be that parent process, okay? So yeah, we're gonna, the way that you can do multiple things is like, you just say this, you're like, if call fork, if fork is equal to 0, then do thing 1, because that means we're in the child process. And then otherwise, else, I don't know the best way to draw this, else, then you just do thing 2, because that means you're the parent process. And both of these things will happen in parallel, because the child will be running this code, the parent will be running this code, and they'll be happening at the same time, because you have 2 copies of the same program running at once. Well, isn't that cool? Isn't that cool to think about? All right, so yeah, if you want to like take advantage of all 4 cores, if you have 4 cores, for example, you want to fork the parent 3 times, okay? But yeah, after you fork, that means the parent and the child, they're 2 versions of the same program running at the same time. Isn't that crazy? So let me prove to you that you can do this and that it's useful. All right, so for first example, let's just like print out from both the parent and the child and say, hey, we're both running at once. So we'll call it fork.cpp. We'll do it in CPP, in C++. So if I want the fork function, which is going to wrap around a fork syscall, it's going to live in unistd.h. I think that stands for like Unix standard or something like that. And that's for fork. And then eventually we're going to ask the program to like the parent to wait for the child to finish, and that's in this header file, sys/wait.h. So we might as well have that one included and ready to go. That one is for wait. Okay, but let's just do fork right now. So let's let's do exactly what I just said. So if forking, if it gives me back 0, so this call right here will duplicate the process. The child will see 0, the parent will see something other than 0. So this if else will be running one body in one program and the other body in the other program. So if we get here, we're the child, and if we get here, we're the parent. Okay, that's the idea. So, what's the best way to do this? Yeah, let's just print out like, hey, hello from the child or something. And we'll do endels to flush the output, just to make sure it's going to work. Hello from the parent. And so technically, when I run this, I will see hello from the child and hello from the parent printed out, but one version of the program is going to run this, the other version of the program is going to run this. We have no control over which core is going to print first. And so, in theory, you'll end up seeing both of them in arbitrary orders. Hello parent, child, parent, child. See, there was child, parent. You see it? So you can control this, all right? Or sorry, you can't control it. It's just like however the operating system is going to schedule it. If you want something to happen later, you can usually like make one of the people, one of your processes wait for a little while. It's called there's a sleep. Oh gosh. So where's fork? It's in section 2 of the manual. So I want to do man2 sleep, I think. No, okay, I don't know how to do it in just a manual page, but C++ sleep. There's a function, and I forget where it lives. I know you can do that in C++. Okay, it also lives in unistandard.h. So there's a usleep function that will have the program sleep for a little while. Okay, so that's the idea. If you wanted the parent to like wait a little while longer, you can be like, there's also just a sleep that sleeps for a certain number of seconds also. So you can be like, sleep for a second, parent, to always make sure that the child like is gonna wait before it prints. So that then you'll always see the child first, for example. But yeah, usually you have no real control. And so most likely that'll be the order, but in some weird universe, you might see this first still, because the CPU cores are waiting for forever. Okay, so that's how you can use fork. You're running two versions of the program at once. It's copying itself. Okay, and what other things can we do with that? Of course, like the whole idea of having a multi-core program is that you can do two things at once and save time that way. So one thing that you might want to like parallelize is you have some big giant array full of values, and you would like to like sum them up, for example, and you can have the child sum up half, the parent sum up half, and then you can just like sum up the two answers from what you see from them. That'll help you like go through the array twice as fast. I hope that makes sense. Okay, so let's make a giant array. Be like let's make an array on the heap, all right, of a certain size. So here will be the size of our array. It's going to be 10 million. And did you know that in C++ you can put little dashes to separate your numbers? That's pretty cool. And then we have, let's make an array on the heap of that particular size, so you can change that. And let's just say that we have garbage memory in here. Let's just use garbage memory, it doesn't matter right now. But let's say we filled this somehow and we want to sum it up, all right? So in the child, we can sum up the first half. All right, we can go like this: for int I equals 0, I is less than size over 2, I plus plus. We can add into our version of the sum variable, because we'll each get a copy starting at 0. You kind of see the appeal of this now. So you can have that summing there, and then the parent can also work on the other half, starting at index size over 2, all the way to size. It'll work on the other half into its own copy of the sum variable, and then they can each like do their fair share. All right, and then you can get back an answer. There's a way for the parent to talk to a child, and then there's also a way for the parent to wait on the child. If you say wait and you call it with null, the null pointer, oops, that lives here, that tells the parent to just wait until one of its children exits. Since we have one child only, we're good to go there. And that's one way to like wait on the child to complete before we do anything extra. So the parent should wait for the child to exit. That's just good manners, okay? We're in charge. We're the grown-ups. So if you say wait with the null pointer, that just tells C++ to wait for at least one child to exit, because it knows about them. It knows they existed. So yeah, again, we're running a program and copying it and doing two things, okay? I'm going super fast. Two things at once. And apparently it doesn't really take very long for you to sum up giant arrays. What if I try 100 million? I might run out of memory though. I'm scared. Whee, that's gonna be how many gigabytes? 400 megabytes maybe? We'll see. No, it's still super fast. Okay. Yeah, so you'll have to... You can imagine that there's a fancier program somewhere that you can think of, but yeah, that's one way to do it. It's twice as fast than it would have been otherwise, that's for sure. Okay, so that's fork. You'll see more of this in like an upper division operating systems class. All right. Next, let's talk about hyper-threading, because that's another thing that modern day CPUs do. So let's see. What was I gonna say? So yeah, I think I forgot to draw more to this picture. Just like it was the fork syscall that did it. We forked it, the parent, into a copy of itself, and we called that the child. Okay, on to hyper-threading now. This is just a fancy term that was, I think, coined by Intel. So there's a more generic term for that. Okay, so first of all, we need to talk about threads. Every process contains one thread of execution at least, okay? And so every process has at least one thread of execution that is like, it's got code to run, global memory, and a heap and all that, and then it's got a stack for that one thread of execution, okay? So it holds the stack for like your main function and all that, but you can actually have multiple threads in a single process. So technically, forking is kind of, it's overkill a lot of the time. It's very heavy-handed to duplicate your process. Sometimes you can just add another thread to share all your current memory. You don't have to copy everything. So you can have multiple threads in a single process, and that will allow them to share memory. So like here's your process. You can have, there's always at least a thread 0 running, thread number 0. You can make a thread 1. And thread 1 will have access to all the memory that belongs to thread 0, like the data section, all your global memory. You can keep that and keep that along for the write. Okay, so that's different from separate processes which have their own copy of all of this all over again. Okay, and yeah, just like for processes, multiple processes, the operating system schedules individual threads to run at the same time on different CPU cores. And so here's kind of what happens if, like, this is a normal program that's only having one thread. That's what happens with what it looks like in memory when it runs. If you make a program with 2 threads, it has all of this, like the same code, the same global data, the same heap, but it has 2 stacks running at the same time, because you have 2 versions, two programs essentially, 2 pieces of code running, 2 execution states, if you think about it that way. So they're running at the same time and they're sharing memory, which is a lot of the time what you want, sharing memory. So that's pretty cool. Okay, and then hyper-threading is the idea of doing threading in hardware. Okay, so hyper-threading is Intel's fancy term for hardware multi-threading, and this is when you make a processor, and you know that processors sometimes don't have a lot to do because they're waiting on memory, or there's like a stall in the pipeline or something, and so sometimes, if you do it right, you can have a single processor core that's capable of hardware multi-threading, and that means it can run multiple threads at the same time, even though it's just one core, which you think it only has like one ALU, one bunch of registers. So that's letting it use everything to its fullest advantage, all right? Everything to the maximum. And so maybe you bought a CPU that looks like this. It's like 4-core 8-thread, because each core can run 2 threads at once. It has some extra power for that ability, okay? So that's what hardware multi-threading is, and Intel just calls it hyper-threading, okay? So that's kind of cool that hardware likes this idea as well. And so hardware manufacturers understand that you're going to want to do this, and they try to optimize the CPU cores these days to run multiple threads, to give you a little bit more bang for your buck, rather than just 4 cores running 4 separate threads. They can run a little bit more, okay? So I think a good exercise for you right now is to go figure out how many processes and threads your computer is running. If you're on Windows, you can run these ideas in PowerShell. This will give you the number of processes, and this will give you the number of threads. And then if you're on a Mac, you can do this. And a similar thing should be true on the Linux terminal if you're running Linux. So yeah, pause the video, try this, see how many processes and threads your computer is running. The number of threads will always be greater than or equal to the number of processes, right? Because each process has at least 1 thread always. So if I go to the class server, let's see. Does this look like it does on a Mac? Yeah. So the first line, we want to get rid of that, and that's what that does. So that's a list of every process running on the machine right now on the class server. And if I count that, the number of lines is 209, and there's a line per process. So there's 209 processes running on the class server right now. And if you do PSAUX capital M, at least on a Mac, you're able to do that. Is that the same? Yeah, so here are a bunch of individual threads as well. Cool. And so you got a bunch of things running at once inside of processes too. Something like that. So close to 500 now, threads. And so you got many processes that are running multiple threads. Isn't that cool? So CPUs are nice these days. They're good at running a lot of stuff at once. Okay, so yeah, for the rest of today, I now want to talk about Git and GitHub, which are very magical places, okay? So go make a GitHub account if you don't have one, and maybe get on the class server if you want to follow along. It will be a fun idea, okay? So if you've never seen this before, you're going to learn a completely new way of thinking. It's going to have a lot of new terms, but you can always just come back to the slides, so don't worry too much about it. But let me try my best to introduce to you the idea of version control. So Git and GitHub wrap around this idea of version control. So Git is it's a terminal command. It's a way to control versions of your software. It was made by the man who created the Linux kernel, Linus Torvalds. So very smart man. He's done a lot of cool stuff. And yeah, what Git is like, it's like Dropbox. It's like Google Drive or OneDrive for your code, but cooler. It's made with code in mind. Okay, so it's going to track all your changes, so you can like go back in time if you need to. It allows you to like write little notes about what changed, what you worked on. It lets you share your work with other people. Lets you branch off from the original code in as many different ways as you'd like to. So it's kind of like you can fork your process. You can fork your code. And yeah, I'm going to make a brand new Git repository. That's just a place where you put code. It's a unit of version control stuff, and it's usually at the level of a directory. So I'm going to make a new directory for our current semester. If you're watching this video in a future semester, you can still try this. I think I'll name it the same one, and I'll give you a link to it, and I'll show you where to find it on GitHub once I post it there. But yeah, here's kind of the idea of Git. You have some code, like you can make some changes. You can save that you made changes, and then you can go off and branch and do other things, work on things, and you can also keep the main line of code. It's like different timelines. You have like different versions of the program existing at once, so different versions of your code files existing at once, and then you can branch off from there. Somebody else can do their own things, and then you can like merge your answers back into like the ground truth version of the code that everybody has, and like the other person who was working can also merge their answers back in and like get all the stuff that you changed as well. So there's usually like a piece of the code that everybody sees, and then you can go off and do your own things and bring them back. So that was probably very big, I know. But yeah, let me make a brand new folder for this particular year. I'll make a F24 CSCI 45 Git demo folder, just in my home folder, I think. I'll do F24 CSCI 45 Git demo. All right, and so there's a folder. I can cd inside of it, and it's blank. There's nothing there. So let me get there in both of my terminals here. Oh shoot, I want to go to boop. All right, so I got two blank folders. All right, same folder twice. This is where it lives on my class server account, and I can put files in here, and I can track their changes with Git. So if I say Git is just the name of a command line command. So if I say Git init, that will create a new Git repository. That's what it's called in my current directory. So I'll say Git init. All right, and it's going to say some stuff for reasons. We'll talk about that later. But you can see that my terminal prompt changed. It like knows that I'm inside of a Git repository now. It knows that the changes are being tracked in this folder. Still, there's nothing really there, but if you do ls-a, it made a secret hidden .git folder where it tracks all the changes. So yeah, now we are able to make changes and Git will see them. All right. So yeah, so there's the concept of something called branches in Git, and these are like the lines of versions of your code. So like master is called a branch. You can make your own my work branch. Then you can, like your coworker can make their name branch or something, and you can always bring them back into the master branch. Okay. And actually this little blurb that it said is that master is the default name for the starting branch, but a lot of people have decided to change that to main. There's some controversy in that area. So a lot of people, including GitHub, when you upload your code to GitHub, it'll usually have you change master to main. But by default, still master is the default branch name. That's where like you put your code that should be like ready for everybody to see. Okay. But you can make other branches. That's what these little spin-off lines with different colors look like. Okay, so if you're lazy and you do all your work alone, then you can usually just use the master branch for everything, because you're not like sharing your work. You just want to have different versions of your code. But if you work with other people, you're going to want to make a bunch of different branches, and like you branch off, they branch off, and you bring it into master later. Okay, so if you're ever concerned about where you are or what you've done, there's a git status command. It's always git space what you want to do with git. Git space status shows you like where you are, what's going on, and it'll look and see if there's any changes. It'll tell you if it finds any. I've not done anything yet. So let me add a text file, and we'll see how the get status changes. All right. So vim hello.txt, and I'll say hello world. All right, I'll save the file. So I got this new file in this folder. It's a Git repository though. Git is tracking my changes. So if I say get status now, it's like, ooh, I see that you have added a file. Would you like to save the contents of that file? Would you like to track its changes? Yes or no? And so it's telling me that you could say git add to track those changes. Right now it noticed it, but it has not seen, but we haven't told it like, yeah, that's a file I care about. All right. So what we're going to do is we're going to commit those changes. All right. So it notices the changes that we make, and if we want to save them, it's a two-step process. We stage them first, and then we commit them. All right. So to stage a file, to say that I would like to add this file to the next thing called a commit, we say git add, then the name of the file. All right. So I'm going to say git add hello.txt. Hit enter. And if you go back to get status, you'll see that it's ready to be committed that particular file. If I made another file, I would git add that one after I make changes to it. So there is some shorthand if you just want to like you want Git to notice all of the changed files that you've made in your current directory. You can just say git add dot, and dot is short for your current directory, and it'll add all of the changes, which is usually what I like to do. But yeah, you can give individual files though if you want that kind of granularity. And then once you're done, once you're ready, you have all your files ready to like save the current versions of these files specifically. Then you tell Git to commit the changes. All right, you say git commit, and it'll plop open the default editor, which is sadly Nano on this machine. And what you do is you give a little message and you save the file. It's a little temporary file, and I'll call this initial commit. And you could type multiple lines. You can put as many lines here as you'd like. The first line is special. It's supposed to be a description of your changes. Okay, boop. And so there's no word wrapping in Nano, sadly. So there, I've saved the file, or I've made the file. Let's Control X to save it. Yes, it's just this default thing. And now you'll see that we've made a commit. It's like, ooh, I know about hello.txt now. All right. If you don't want to open Nano, you can do it quickly, just like to give the first line. If you want to write a novel, you'll have to say git commit by itself. But if you just want to give like a commit message that's quick, you can say git commit -m, and then within quotes you can give like your message. Okay. So after I've committed something, git status again. We can always check it. We're in the master branch. Nothing to commit. Everything's been saved. So that new hello.txt file is saved within Git now. We've got that version of it. Okay. And we can use git log to show the history of all our commits. So it keeps a log of everything that's happened. And here is the one and only commit, and it's saying that the master branch is working on this version of the files right now. And like here's the description of what kind of happened in that commit. It was the first one. All right. So let me make some more changes. I'll commit them, and we'll notice how the log itself changes. All right. So let me make a new file. Vim, I don't know, file2.txt, or let's do a CPP file this time. So there's a CPP file, and then let me even change like hello.txt. I'll add another line. All right. So I've changed two files. I've made a new file, and I've changed an old file that we've tracked the changes of. So if I say git status now, dun dun dun, you'll notice that we've modified a file that we've saved the changes on previously, and it's asking, do we want to commit those new changes in a new version of the file? And it also notices that we have a file that we've never committed before. Would you like to save its changes? And so I'll say git add dot to add everything in my current folder that's been changed. And if I say git status, you'll see that they're ready to be committed. The new change to the hello.txt and the new file itself. Okay. So I'll say git commit -m made some changes. I don't know, dot, dot, dot. So cool, now I have another commit. Git log shows both of them, and like here's the original version of the files, and then like here's the addition of the new file and the change to the hello.txt. All right, so it may seem not like a lot, but you can go back to this commit. It has a number, a secret number that specifies what's there. You can go back to this commit if you messed up, and it will take you back to the version of the folder that was there during this commit. That's the beauty of Git. That's the magic of it. You can always reset your repository, your folder that you're tracking the changes on, to a previous version of all the files. And that's what it means to use Git. Okay? That's the idea. So I hope that makes a little bit of sense at least. So yeah, let me talk to you about like branches and using them. All right. So the idea of a branch is that like you have master. Master is technically a branch, and you have versions of the code in master, and you can branch off and do something that like is not really ready for prime time yet, because master is meant to be like the version of the code that can be in production or something. You can branch off from there and make some changes on your own. Dun, 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 while you make other like prime time changes in master. And eventually, you can merge your changes back. That's the idea. Those are the terms, all right? And go from there, all right? So yeah, you can branch off from a certain point of your of the versions of your files, from a certain branch into a new one. And then you can eventually merge them back somewhere, usually to the master branch, all right? So if you'd like to make a new branch, you just say git branch and give it a name. So git branch, like I'll call it, I don't know, test1, sure. So this has taken me, first of all, this has made the branches, not placed me there. All right, if I say just git branch by itself, shows you all the branches that you can choose and where you are. So it shows us that we are in the master branch, but there is also a test1 branch that we just made. If we'd like to go and work in that branch, it's branched based off of our current files, so we'll see them all there still. You will switch to that branch. Git switch, name of the branch. And now we're in the test1 branch. My terminal is nice enough to show that to me. And like ls shows the same files. Git branch shows us that we are in test1 now. And now we can safely make changes and not mess with master. All right. There was another way to switch branches. It was this. Don't worry about it. That's the old way. So now let's edit some files. All right. Let's edit some files, and I'll show you some cool stuff. All right. And we'll commit them too. So let's edit hello.txt, another new line. So add a line there. I will, let's change hello.cpp. I don't know, add a second line, I'm not sure. So I've changed these files. Git status shows that they've changed. I can add them. I can notice that they're ready to be committed. Git commit -m. Messed with hello.cpp/txt. Oops, and I forgot to close the quote. So let me redo that. There. And so now git log shows that I've made some changes. The master branch is still here, but test1 has new stuff. And you can kind of see that from the log itself. So I hope that makes a little bit of sense. So yeah. So I edited the files, and I committed them. Let's see. Maybe I shouldn't have committed them actually, because I wanted to show you git diff. So let me edit hello.txt a third time. Wee. More new lines. I'll add like 2 new lines or something. And so I've made changes to hello.txt. You can see your changes by saying git diff. That shows you the difference between the repository's saved versions of the files in your current branch and your current versions of the files that you have just in the file system. So it shows me that in hello.txt, I've added 2 lines. See the plus sign and the green? So I've added some new lines, and it tells me that. I get to see that. So if you care, like you want to make sure, like, were those the changes that I wanted to make? And then you can like add them and commit them. So I'll add them all. Git status shows me that they're ready to be committed. Git commit -m added more lines to hello.txt. So you just give a description of what you did. All right. So now, if I go back to master, So git log should show me that there's a couple new commits, and these were just on test 1. Master is still stuck here. All those lines from hello.txt are not there if I git switch back to master. Okay, so now I'm back on master, and look, I still have those files, but look at hello.txt. It's the old stuff, okay? Hoo-hoo. So let's edit the file again here. This change was from the master branch. Boop. So let me change hello.txt. Now I have 2 versions of the file if I were to commit this, right? Git diff. Now I've changed this version of hello.txt to that. If I commit that, changed hello.txt from master, git log now shows you that there's some weird stuff going on. So git log only knows things from master's perspective. So it doesn't even know that anything has changed in the test 1 branch, because that would just pollute all of this information. It's too much information at once. But if you have multiple changes, so now test 1 has changes, so like here's hello.txt. In master, if I switch back to test 1 branch, and I output hello.txt, it's that other version of the file. See, I got 2 versions of the file now, all right? So let's go back to master, because that's where you want to put all your code usually. You want to bring it all in. You want to merge it back in after you've done all your work, and maybe things have changed. So your goal is to bring everything back, and like if there are some competing changes, you'll have to resolve that manually, all right? So I'll say git merge. So the first thing you do is you get in the branch that you want to merge back into, so master in our case. So we're there, we're in master right now. And I'm going to say git merge, and then the branch you want to merge all the files from, all right? All the changes from. Git merge test 1, please. And, ooh, it tried to merge hello.txt, and sadly, there were some merge conflicts. It could not automatically merge them because like these changes, it didn't know like which versions did you want. This is the same file, you're messing with the same lines almost. It didn't know what you wanted. And so if it can't do it automatically, sometimes it can, it produces merge conflicts, and you are forced to go into the file itself. So hello.txt, we have to look at that and mess with it and resolve the conflicts. And you'll see that there are some special lines that have been added, all right? And this is saying like left, so the very first thing, this is from the current state of the master branch. It's like the head of, it's like a linked list almost. It's kind of how you think about these branches. Like here's the end of the linked list, essentially. That's where where the head of master is right now. That's what it sees. Here's the new change from master. And then equal signs, and then it's like pointing to the right side is test 1. Here's all the stuff from master, the current version, the head of the master. And then here is the stuff from test 1. What do you want? How do you want to move these around and resolve the conflicts? So your job is to like make the version of hello.txt that you really were looking for. Like how do you resolve this? So maybe it's like, all right, let's put this line here. And like that's the resolution. And then I'll delete all these helper get lines, and like that's the final version of the file that I want. So if I save that and do git status, it's ready to commit those changes. All right, it knows that I changed hello.cpp from the other branch, and like it added that in just fine because there are no competing changes in master. But there were competing changes in hello.txt. Those were unmerged. We've fixed them. We've resolved them. So we have to add it back and say like I'm ready now. So I'll say git add hello.txt, or just git add dot, either one. And it's like I am ready. I am ready. We're still in the process of merging. That's not been finished yet. We have to commit to conclude the merge. That's what it's saying. All right. So git commit merged, or sorry, it's -m merged test 1 into master. All right. Bam. So git log shows me, now we see all the changes from test 1 because they're being taken in, and we see where like we've added a new commit on top of all those ones. All right. And that's how that works. All right. And you can see all of our other commits, and like this is where master is right now. It's got my merged stuff. So if I look at hello.cpp, I see that new version that I took from the other branch, and then hello.txt has been resolved. So yeah, that's branches and merging in a nutshell. There's a whole lot I know to talk about, but this is the beginning of it all. It's very cool stuff. All right. Next, we can bring this all on GitHub. GitHub is a website that lets you host your Git repositories so that others can see them. Okay, so go make a GitHub account if you don't have one, and I'm going to make a public repository and push, that's the technical term, I'm going to put this folder that I just made on Git, all right, from Git on GitHub. So I'll go to the GitHub website and I'll make a new repository that's public for you guys to see, public, and I'll call it the same name here, F24 CSCI 45 Git demo, bam, and I'll click create repository, and then I'll add all my changes, and it was an existing place, and so I'll follow these lines. I'll say git remote. I'm just gonna paste what it says to do here. It's like, all right, add it to GitHub by saying that, and then this is a line. GitHub likes, instead of master, it calls it main, so this line is gonna change my master branch to main instead. It's gonna rename it because it likes that instead, so that's a little confusing, but that's something that happens. And then if I type this, push, it's gonna shove all that information from the repository onto GitHub, all right? And so now if I refresh this page, I have uploaded all this code, and this is where it is. This is the website. This is the link to it. I can put this in these slides here. So, dun, dun, dun. Oh gosh, nope, not there, not there. Dun, dun, dun. So yeah, after you make a GitHub account, here, let me just do this real quick. I'll give you the link to it. It's right there. There's the Git demo repository that you should be able to see. And after you make your account, you're going to need to make a personal access token for yourself. All right, so follow that link, do it, and then you're going to have to tell Git about yourself, like what's your name, what's your email. You can also make something up, but that's just like that's included in every commit. Like I've already done that. That's what you see in Git log. So he's like, okay, this is my name that I configured with Git. This is my email that I configured with Git. Yeah. So you can put that however you want it, and then you're ready to get my code. You can look at my code if you'd like. All right, you can see all this, and the beauty of Git, remember, is you can see all the versions. Like here are all the commits. You can see all the changes. This particular change, what did it do? It added these lines. Isn't that so cool? And you can go back to all the old versions. Remember the very first version with just hello world? You can see all of them. Each commit is the granularity that you get to see. All right, so every time you commit, that's the changes that you're remembering. So you can commit often or commit not very often. It's up to you, but you should probably commit often, more often than not often. I hope that makes sense. All right, that's a lot of me saying often, but yeah. So once you've made a GitHub account, there's a cool thing that people like to do in the open source world, and that's called forking a repository. All right, so what you should do for this example, go to this link and you can click fork on my repository. In the future, when you work with your partners in like this particular class, I want you to use private repositories, but because I want to show you like the magic of like open source development on GitHub, I've made a public repository, but please use private repositories for this class. But I made a public one, it's this one. You can go to the link and you can fork it. You can click the little fork button, and that makes your own personal version of the repository. I don't know where I want to put it. I can't really put it anywhere, I guess. Can I give it a new name? Git demo fork, I'll call it something different. And then, darn, I can't give it to my own. I can't give it to my own account. But if you click create fork, it'll let you create a fork. I guess let me give it to my class. So there. I have the ability, you will too, and if you click create fork, then you have your own personal version of the repository that you can work on, all right? And then you can get all the code yourself, all right? So you want to then get it onto your own machine, you'll pull it over the HTTPS protocol, all right? So here's the secret. Here's how you get the files back on your own terminal. So get on the terminal somewhere, get where you want to store your repository. Let me go up here, I guess. Let me go to my home folder, and I'm going to say, here's how you do it. Here's how you say, I would like, you've made your fork, you go to the code button, and then you click HTTPS, because that's going to go and use your personal access token. You'll copy that HTTPS link to your clipboard, and then you can say git clone. All right, this is how you do it. You say git clone, and that creates a copy of it. Git clone, and then you give that particular URL, and then you hit enter, and that will get your version of the fork. All right, so The username is your GitHub username, and the password is the access token that you made for yourself. When you do make that access token, by the way, you have to check some permissions, and one of which needs to be like the ability to clone something and to push to GitHub. So search for those words. That should be something that you allow when you create this personal access token. I don't see exactly. It's like repository access. I think maybe permissions. But yeah, you want like repository permissions for sure, probably account permissions, but hopefully the page will help you, okay? So make that personal access token that lets you clone the repository. So you'll say git clone, and this, oops, sorry about that. You'll say git clone and get this URL, and that will make that version of the files everything from here, it'll bring it onto your own machine. I've actually configured SSH for my particular account, so I'm going to clone like that instead, but you want to use your access token. All right, so it's cloning into here, and you see that it's made that new folder, whatever you called it. It'll probably be, if you just kept the default, CSCI 45 git demo, but I have two versions right now. I have my fork and I have the original. So I can cd into the fork. Boop, so there's that. And you can see that I am in the main branch of that repository, which got renamed for master. Remember, git log has all the changes still. They were still my changes. You'll have my name there. But you now can make your own changes. All right, so what I'd like you to do is make some changes, add a line to one of my files, or create a non-empty file, or like put an image up there, whatever you want. And then commit it, all right? I'll do it myself as well, but give yourself some time to try that and see if you can get practice, like make a branch, merge it back into, now it's the main branch though, so keep that in mind. But yeah, see what you can do, play around, and I'll show you how to get it back up into GitHub, okay? All right, so I will make a change to, I don't know, which file? How about hello.txt? Hello from Lawton's fork. And you can add your own lines to this file if you'd like. Say your name, say that you've been here, and then we're going to commit that file. So here's kind of like the setup. You cloned the file. You said git clone. You clone the repository on your end. You gave it the URL. That's supposed to be an R. And that gets it on your machine for the first time, your version of the repository, and then you can keep it in sync in this way. So like here is the server where it's being stored, so that's GitHub. They have a bunch of servers where they're storing your versions of your repositories, and then you have your own computer where you just cloned the repository. In general, when you get something from the server onto your computer, it's called a, let me put it over here. It's called a pull. We pulled it down from the internet. And then when you'd like to give your changes back, it's called a push. We push it up into the server land, okay? So after you make your changes and you commit them, git status, all the fun stuff, add that new version of hello.txt, git commit -m changed hello.txt from my fork. It's committed. Git status shows that it's been changed. You can do this in a branch if you'd like, but have fun. Then we'll commit it, all right, and give a description. Maybe I should have said my name or something. So add all your changes, commit them, and then what you do is you push the changes. Due to the way that you got them, the way that you cloned it, it knew where the website was and everything. You can just say git push, it has it saved. So you say git push, as well as it's telling you about this now. After you say git status, your branch is ahead of the server by one commit, you can push it. So say git push, and then it's pushing it on to the internet. And if you refresh your version of the fork, you can see that, like, oh, it changed now. There's hello.txt. Here is my change and all that. Okay, so you've made your changes, and the way that open source software works these days is you create, once you've made your changes, you make what's called a pull request, which is just, it's like a message to the original owner of the repository, so that's me, because we forked it from me. We make a little pull request to say, like, I'd like you to take my code. Please pull my version of the code because I've made cool things. I've made cool changes. Okay? So, yeah. You create a pull request like this. You go to the pull requests tab, you say new pull request, and you can give it a name. But you click create, and let's see, is there anything else I want to say? This is just like, it's going to send a message to me, the original owner of the repository, to say that I should take your stuff. All right, it's like, this is your one commit because you've changed one file and all that. Create pull request. It's like, I changed that from my fork. Pull me, please. I don't know. Create pull request, and then it goes to me. Okay, that's the idea. And so that's how that works. And then it goes back to the owner of the original repository, and it's like, I want to change this. And this is something I see on my end, okay? I have the ability to merge it back. You do not, okay? So let me merge all of your changes, and merge, confirm merge. And then after you've made changes, after I pulled all your changes and like I've changed the actual repository from all my students' different things, you can go back to your fork, and where's that? Boop. Nope, it's still not there. What did I call it? There it is. So there's the fork. There should be a button called sync fork, and you click update, and you get the current version of everything, update branch and all that. Okay, so that's kind of the idea. So you click sync fork to sync with the original repository, then you can make more changes, new pull requests, and all that. So that's how you stay up to date as you're doing open source software development. That's what people do these days. So that's kind of cool, isn't it? So that's more or less how Git and GitHub work. It's a very, very short introduction, I know, so there's plenty more to it. But I believe that with enough practice, you'll get good at it and it'll all make sense. So I highly encourage you, if you're working with a partner in this class, to use GitHub. All right? I highly encourage you to use Git and GitHub when you're working on your labs with a partner, because then you'll both be able to push and pull code, maybe use separate branches even, bring it all into the main or the master branch at the end. Like, that's a very easy way to share your code with your partner, okay? Do not do what I just did. Don't make a public repository and ask for pull requests. That is not correct. I do not want to see your code available on the internet. Make a private repository instead. Every GitHub account is allowed to make private repositories. Put your code on there, and then you'll just give access to your partner. And I can absolutely help you guys. Please, though, please, 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 make private repositories and not public ones for this class, okay? Except for your final project. When you're working on your labs, I want private repositories only. And then you don't actually have to fork. You just like share, like the owner, one of you who made the repository, can just give access to the account name of the other person. And then you can push and pull to the same place. You'll have that same repository access for yourselves, okay? Keep in mind that I do not want to see any public repositories with your lab data. All right, just read that bullet and read it well. That is, I think, all that I want to say about Git and GitHub. So yeah, to make your own new private repositories, you'll go and let's go back to like the home page. You just click the little new button, new repository, give it a name, and you'll click from public to private. Okay, public to private. Click the lock, please. So yeah, that is Git and GitHub in a nutshell, in addition to some other stuff, of course. But yeah, you've learned a lot. Go forth and use that knowledge to do cool things, and I will see you next time.